I'm gonna admit everybody. Okay. So welcome everybody to this set. I'm very pleased to introduce today to Teddy Mekonnen, who's going to talk about competition, persuasion, and search. It's a joint work with Bobby Pakzad-Hurson, who's also here and is going to help us with questions in the chat. And we have as guest panelists Alessandro Bonatti and Mark Whitmeyer. So thank you all for joining us today. So just as a reminder, next week we have Piotr Warsak, who's going to talk about the mechanism design approach to property rights. Well, Teddy, thank you again for joining us today. The screen is yours.
Thank you so much for inviting me to do this. I really appreciate it. And thank you, Alessandro and Mark, for agreeing to be panelists. This is the first time I'm presenting this work. So all feedback is very, very welcome. Anything from notation to terminology to things that are a lot more substantial than that. Everything's on the table. So the paper is called, at least for now, Competition, Persuasion, and Search. And here's kind of the idea that we have in mind. I'm going to start with just a motivating example. So imagine you have a firm that wishes to fill a vacancy and searching for an employee. And what the firm wants is a highly productive employee, and they would like to find the employee sooner rather than later. So they want to find a high quality, high productivity worker, and they want to find it as soon as possible. And you can think of this as a very simple search problem. In fact, this is kind of the ideas behind the McCall search problem. And the way you can envision this is, the firm posts a vacancy. A worker arrives each period. The firm is going to interview the worker, which provides some source of information about the worker's productivity that the firm gets to observe. And then based on that information, the firm is going to decide whether they're going to hire the worker or continue searching. But in reality, when you post a vacancy, a worker arrives, you interview, and maybe you get a sense of their productivity, but often it might look a bit like this. So you think you have an idea, but it's a little blurry, it's not quite clear. And in fact, this is the case in many US firms. So especially for low service workers, more and more US firms are turning to what are called pre-employment tests. Essentially, and whenever a worker arrives, you're going to send them to go get tested. And this could involve cognitive assessments. It could be job-related skills such as, how good are you at talking to customers? How good are you at de-escalating tense situations? They kind of put you through a battery of tests, and then these information brokers will come back to the firm and make a recommendation of either hiring the worker or not hiring the worker. These tests tend to be quite decisive for these kind of low service jobs. So it seems that in this search process, the decision making about whether to hire or not and the information processing have been decentralized. So the firm is still going to be the one that retains the agency in choosing whether they're going to hire a worker or not, but the information is being provided by an outside party. And that's essentially the problem that we want to study. So think about the standard McCall search. The way it works is there's a single agent. Each period, they're going to randomly sample a good from a search pool. Upon randomly sampling this good, they're going to observe the good's actual quality. And then the agent is going to decide whether they're going to stop searching or they're going to continue searching, and searches without recall. So this is a very simple problem where you essentially have a threshold rule. If you ever see a quality above a particular threshold, you should stop searching. If it's below, you keep searching. And this is going to depend, this threshold will depend on the kind of the general distribution of quality within the market, as well as how costly it is for you to keep searching. So what we're going to do is focus on the second bullet point, that the agent is observing the goods quality. We're going to replace that by assuming the polar opposite, where the agent, in fact, cannot observe anything upon sampling. What they can instead do is they can contract with information brokers who sell them information. Okay. And we're interested in studying this relationship between information brokers and this agent that is in a search market. So the setup is as follows. It's a repeated contracting problem that has been embedded into a sequential search problem. So in each period, just as before, the agent is going to randomly sample a good from a search pool. But now there are going to be n principals greater than or equal to 1 who choose the supply and the price of information that this agent is going to be able to see. And the agent's choice is to either buy information from one of these principals or to not buy information. And then based on whatever the agent gets to observe, they choose to either continue searching or to stop their search. Okay. So this might seem familiar. This is we have another paper that lives in this very same world. So this one is with another co-author who used to be a graduate student at Brown, Zeki. And in that paper, we consider the case when there's only one principal and one agent. And what we did in that paper is we focus only on stationary equilibrium outcomes. And we show that there's an essentially unique stationary equilibrium outcome, and it involves the principal essentially extracting the full surplus from the agent. Okay. Now, the focus of this paper is going to be more about the tensions between monopoly and competition. So we want to do a comparison across equilibrium outcomes in monopoly versus the equilibrium outcomes under competition. And we want to ask how competition affects the level of information that's being provided to the agent. Now, in our world, if you want to think about efficiency, the only surplus that gets to be generated is whatever surplus is generated in the search market. So whatever information is provided, it's only useful in that it helps the agent search better. So the more information that we have to search, the higher the efficiency is going to be. But because we also have this transferable utility between the agent is paying for information, it's not immediately true in this world that just because the agent receives more information doesn't mean the agent is immediately better off. Okay? If you had non-transferable utility, then a single agent problem always benefits from having more information. This is not necessarily true in our world. So we also want to look at how competition is going to affect the agent surplus on top of how it affects the efficient outcomes. So what we find is that there is actually a tension in this model between competition and between efficiency and the agent's welfare. What we show is competition, in fact, is going to reduce efficiency, but it is going to raise the agent's surplus. And what we're going to do in this kind of comparison across monopoly and competition is we're not just going to focus on a particular equilibrium that might seem attractive or tractable, but we're going to do a comparison across all equilibrium outcomes. So you should think of this as saying the efficient outcomes that are achievable under competition are generally lower than the outcomes that are achievable under a monopolist. And you have the reverse for the agent's surplus.
Teddy,
Now,
can I interrupt you for a second?
Yep.
So this is just related to the statement you have on the screen. And this is kind of anticipating probably where you're going, but the naive intuition would be, I mean, in some sense, this is surprising given that it's more or less a repeated game between the principals. And so I wonder why they can't just sustain a collusive equilibrium where they get the monopoly outcome, which of course fully extracts the surplus. I mean, can you hint at why that might not be so here?
So you with a loan of cost of search, which here translates to kind of think of it as a high enough discount factor, you will be able to have these kinds of collusive outcomes. The issue is with a monopolist is essentially able to achieve efficiency all the time. So if you only kind of think about the Pareto frontier that they'll be able to achieve, the monopolist equilibrium will always be there. Whereas with competition, because you have different collusive behavior happening, Sometimes it might be on the Pareto frontier, but sometimes you can have equilibria that are actually quite far away from it. So when you do the set comparisons of the total surpluses you might be able to generate with competition versus with just a monopolist, they could actually look quite different because of that.
Thank you.
Okay. So how do we kind of show this? Well, we're going to get to this result by through a series of smaller steps. The first is we're going to characterize the entire equilibrium payoff set when you only have a monopolist. And this we thought was an interesting thing for us, but as an aside, it has an interesting structure, which is very bang bang. So it's either going to be a unique outcome or it is going to give you a folk theorem result. And the next thing we do is we partially characterize the equilibrium payoff sets for competition for any n greater than 1. And then we're going to compare the surpluses that are generated in equilibrium as well as the agent surpluses that are generated in the equilibrium of these two different settings by essentially focusing on the infima and the suprema of these sets. Okay? So the set comparison that we're going to use is actually stronger than just using strong set order here. And I'll get in a little bit more detail in just a minute. Okay. So this is the general idea. I'll pause here for a second if there are any questions. Okay.
So Teddy, I couldn't help think a little bit about applications. Yale just announced their new president, and a bunch of schools are looking for their deans. So as soon as you give me an intermediary in a search market, I think like a CEO search firm or one of these scouts. What they do is definitely provide information. Yep. They do not make hiring on behalf of the agent. But they actually sort of they come up with the prospects, right? They give you a list.
Yeah.
So I'm just wondering how you're thinking about this problem and whether, because what I'm saying is that here the agent on the samples a good in every period and then gets the information. It doesn't really matter who sampled the good in this world.
Yeah.
Are you thinking that this could accommodate principles generating the options themselves?
I see. So that's a good question. I don't think this is, at least the setup that we have currently is a good setup for that. So I think there's interesting strategic interactions that you could embed into this model by allowing the principals to not necessarily just choose the information they provide, but also choose the underlying distribution from which the agent draws. And then you can think about, what are the incentives for the agent to either continue searching or to terminate their search earlier based on that distribution that they're choosing. And we haven't really thought about that. I think that is actually a feasible tweak to the model that you could explore here, but we haven't done that. So that's a good idea. Okay, thank you. Okay. So the roadmap is the following. I'm going to detail the model, and then I will present what the main result is at the very get-go. And then I will go through some preliminary steps that are going to be very helpful in setting up the problem, and I'll provide you a rough-ish sketch of the proof. This is, again, the first time I'm presenting this, so please, if things feel unclear or some parts feel clunkier than others, let us know so that we can kind of polish this up as well. Okay, and then at the end, I will conclude by talking about the related literature. Hopefully, I should have time for that. All right, so the model is the following. It's, as I said, it's going to be a repeated contracting problem that is embedded in a quitting game. So we have a game between an agent who we'll refer to as he and n principals who we'll refer to as she. So this capital N is just the set of the principals index. There's also going to be a continuum of goods with heterogeneous quality, and quality is going to be denoted by theta. We are going to normalize it so that it's in 0, 1. And it's going to, each good's quality is drawn IID according to some absolutely continuous distribution F. So this would be, for example, the tweak that you can add to this model if you had in mind that the principals can also design the search pool as well as the information that the agent gets to see. But for us, we're going to hold this fixed, and we're going to denote the prior mean, which is the expected quality given your prior belief F, to just be M naught. And the substantive assumption in the entire paper is that this theta is unobserved. It's unobserved by the agent, and it's also unobserved by the principal. So they're not conditioning the signals that they provide based on the actual quality of the theta itself. So the agent has a unit demand, and he's going to search sequentially without recall. So here, the without recall part is actually without loss of generality because you have a continuum of goods. And the way search works is each period he will incur a flow cost of K, and he will draw one good from this search pool at random. Okay? We're going to assume that K is less than the prior mean. This is just to ensure that the agent actually wishes to engage with search. Yes?
Oh, yeah, I mean, so what do you mean there is with a loss of generality? Because, you know, if you keep on searching and, oh, I see. So what I was having in mind is that maybe you got something better in the past, but I guess it's because you search and you stop only when you go above a certain threshold. Okay, sorry, fine.
Absolutely. So I guess I should be a bit careful. So if if you're looking, for example, at stationary equilibria, then it would be without loss of generality. If I, for some reason choose a really bad continuation equilibrium and the agent wishes to go back to find something that was actually better, that could happen. So then this assumption of without recall will have some bite. Absolutely right. Yeah. Okay. So these are essentially the steps that the agent has. He has a unit demand. So the minute he finds something he wishes to consume, the game is over. What do the principals do? Well, each one of them can design any signal, which is a Blackwell experiment, that maps the true quality of a good into some distribution over messages M. And here we're just going to look at unbiased signals. This is without loss of generality. It just means that the message that you see will have the same label as the type space, and conditional on observing a message M, the agent's posterior belief, posterior expectation of the quality of the good is M itself. Okay, so I'm just going to say this quality is this good is of expected quality M. That will be the message that I send, and we're going to have the signals confirm that exact message by base updating. Now, I haven't said much about payoffs yet, but we're going to assume that all the players are risk neutral. And in fact, the only thing that's going to matter here is the posterior mean. What is your expected belief of quality? What is your expectation of quality conditional on the messages that you see? So for our purposes, it's going to be sufficient to just consider distributions over these posterior means as the signal itself, instead of thinking about these pies that are these Blackwell experiments. So what is a posterior mean distribution that can be induced by some Blackwell experiment? Well, Blackwell has answered this question for us. It's going to be any CDF that is a mean preserving contraction of the prior belief F. What does that mean? That's just given by this set of integral inequalities. This is a majorization constraint, essentially. Two types of mean preserving contractions that I want to highlight. When the agent gets full information, then the distribution over posterior means we induce is going to be exactly F itself. So if I ever write that the agent is searching with an information signal of F, that means he has full information. In contrast, if the agent has no information, the only posterior mean that can be induced is just the prior mean. So the CDF that has weights an atom 1 exactly at the prior mean, I'm going to denote that by G naught. So that's signifying no information. And I will describe the set of all mean preserving contractions by the script of G of F. Okay. So this is useful just because, as I already mentioned, Blackwell, Strassen, and Econ, Rothschild, and Stiglitz have shown that there's this one-to-one kind of mapping between these Blackwell experiment signals and these mean preserving contractions of the prior. So we can just think about signals as just these mean preserving contractions instead of thinking about them as these experimental maps. So each principal in each period will make a take it or leave it offer to the agent. An offer, excuse me, is going to be a pair of a price, P, and some posterior mean distribution, G. The profile of offers that the principals offer, I'm going to just denote that by capital O. And one extra thing here is that the agent always has access to what we're going to call the null offer. And this is an offer that has a price of 0 and an information of no, and a distribution that is the same as the no information posterior mean distribution. Okay? So,
Teddy,
yes?
this is a bit of a cheap question. But how big of a restriction is it, the take it or leave it offer, rather than say a menu that you could say condition on the realized draw? I understand, one answer is that it's more realistic, right? But to just have the flat price, but
so I mean I don't know enough to be able to say, for example, that is without loss of generality. In the previous paper that we've worked on, it actually didn't really, so the stationary equilibrium characterizing that, it was the prices and the information that you might induce in equilibrium might change if I allow you to condition on the realizations themselves instead of just giving a take it or leave it offer. But the equilibrium payoff that they induce were all going to be the same. So that's essentially what I meant by the stationary outcomes were essentially unique in that paper. I don't know what happens here. Yeah, so we're making this assumption that it is a take it or leave it offer that's just a posted price.
all right.
But I mean, I suspect you've worked on this for so much longer, but I suspect you'll be able to make some progress, right? Because the thetas are the prospects are IID.
Yep.
And so presumably there's some realization in equilibrium. There will be some realization of these signals that makes me stop, and some continuation value that depends on the future prices. So it feels like in equilibrium you could change this. You could at least reformulate this to only paying if you hire, but I'm maybe that screws up something down the line. Either way, I think it's.
So there's this particular thing that happens. So from the principal's perspective, they don't really care because they just care about the average price that they're going to get. From the agent's perspective, I think whether you're paying, for example, if you pay an upfront fee, then, and you anticipate paying an upfront fee in the future, it's essentially reducing your continuation value. So it might make you want to leave earlier. On the other hand, if I say you don't have to pay anything until you decide to stop, then you want your threshold to be a lot higher because you want it to be worthwhile.
You're right.
And so like there's these kind of the agent's incentives on how they want to search changes. So we have to be a bit careful there.
You're right. Thanks.
Okay. Okay, so and then the null offer is basically just to guarantee that the agent could always say, I don't want to buy information from anybody. I'm just going to go without information for this period. It's just a convenient way of notation for us. Okay. And then given a profile of offers that the agent sees, he is going to accept the take it or leave it offer from at most one principal. And we're going to denote this by choosing a W. So this is his purchase choice from either one of the principals that's in capital N, or just picking the null offer. And once he picks an offer to purchase, he pays the price P associated with that particular person's offer, and he's going to publicly observe the signal realization of this of the signal that he purchased. Okay, so I've put these two things in red because there are assumptions that I think are worth discussing. So the first one is the agent is only buying information from at most one principal. And what this is ruling out is the agent being able to purchase signals from multiple principals simultaneously, and then combining the realizations of those signals to learn a lot more than he would be able to if he could only observe the signal of only one of the principals. Okay? This is the kind of signal combination that you can engage in, for example, in Getzkow and Kamenika. Now, I will discuss in a bit that the outcomes that we're looking at, the equilibriums that we characterize, actually do not require, if we were to allow the agent to purchase signals from multiple principals, it would still be optimal for the agent to not do so. And the reason is the equilibrium signals are effectively deterministic signals. And therefore, if you purchase it from multiple people, you're just going to be learning redundant information, and therefore you don't do that. Okay. The second thing is that the signal realizations are publicly observable. This effectively means that the only uncertainty that there is going to be in this model is about the quality of the good that's been drawn. Okay, so all past actions are going to be perfectly observable, and again, this isn't going to play much of a role. We could assume that the agent privately observes the signal realizations. The equilibriums that we construct are not going to depend on the principles using the signal realizations as a way of kind of managing the agent's continuation value. The only thing that would change if we made this private information is that now we have to keep track of a public history for the principals, a private history for the agent, and then some sort of a belief system for the principals about what signal realizations the agent might have seen in the past. But obviously, these are IID things anyway, so they really aren't going to play much of a role. Okay, so this is the timing of the game. It's a discrete time game. In each period, the agent first incurs a cost K and draws some good of quality theta T according to F. And this theta T is unobserved by everybody. The principals are going to simultaneously make offers to the agent. And then given this profile of offers, the agent will choose to buy the take it or leave it offer from one of the principals, or to not buy from any. Then he observes a signal realization according to the choice of his purchase that he made, and he chooses whether he's going to continue or stop searching. So the game tree looks a little like this. He first samples the good, he observes a sequence of offers, and either he buys, let's say, from principal J, or he chooses not to buy. And if he doesn't buy, the only belief he will have is that the good is the expected quality of the good is the prior mean. On the other hand, if he buys it from principal J, then he's going to observe some signal that is distributed according to the signal that principal J is selling. After seeing these signals, he either chooses to end the game, which means the search is over and he consumes the good, or he continues searching again, in which case we'll just repeat this whole game all over again. So the ex post payoffs are as follows. Principal J only gets revenue if the agent buys from that principal, and the agent's ex post payoff is Well, if he chooses to consume the good, he enjoys the utility associated with that quality. He has to incur the search cost in each period, so there's a minus K, and whatever price that he pays for the privilege of observing the signal. Okay. So in this, we're going to look at the PBE of this game. And as a standard, this is just going to require that strategies are sequentially rational, and there's some belief system that is consistent with base rule. I want to point out that the second bullet point is actually not necessary for us. And the reason is, as I said, the only uncertainty that exists in this world is only about the good, the quality of the good. So all past actions are perfectly observable. So if we're ever at an information set that we're not expecting, so if one of the principals makes an offer that we did not expect, and we allow for, we impose the no signaling what you don't know, then the agent should not be inferring anything about the quality of the good just because the principal deviated, since no one knows anything about the quality of the good in the first place. On top of this, the strategies of the principals are effectively just determining the distribution of the beliefs that we're going to have anyway. So beliefs are encoded into the strategy space as is. So having another specification of a belief system in this setting will be redundant.
Teddy, can I ask one question about commitment?
Yep.
So within each period, there is commitment because there's an offer. So it's not a cheap talk offer. It's I have a policy of and I can review. But then the strategies are sequentially rational, so I cannot commit to do anything in the future period.
Yes.
How do I square those two things? Maybe this is just a question about the motivation or a good example rather than technicality, obviously.
Yeah, so I think in many of these, in the motivating example, in some of these relationships, you see that there's a long-standing relationship between the pre-employment tester and the firm. But in others, there's also cases where even if there's a long-standing relationship, you're paying per customer for, you're essentially paying per employee that you get tested. And there isn't a long-standing contract between these individuals. Essentially, you have some menu of tests that you get to pick from, and then you say, I would like to have these battery of tests performed. And tomorrow, it might be that you have a different type of employee you want tested, and you would like to have the flexibility of choosing something else. So I think you're right that in some instances, you have commitment, not just within period, but long-term commitment. And in others, you don't, and we're focusing on the latter. Absolutely right.
Gotcha. Thanks.
Okay. Okay, so we're going to look at the PBE payoffs. Let's denote those by the script E, and I'm going to parameterize it by the number of principals as well as by the flow cost of search, so N and K. So you take any vector in this, any payoff profile in this set, Yj is going to represent principal J's payoff if this J is less than N, and the nth plus 1 component of this vector is just going to be the agent's payoff. Okay? So I'm just writing the principal's payoffs first and then finishing off with the agents. So what are our main results? First, I need to tell you a little bit about how we're going to compare different sets. So take two sets in R on the real line that are not equal to each other. We're going to say that set E dominates set E prime if the smallest value of E is higher than the largest value of E prime. Okay. So this is one example where set E dominates set E prime. This is an example where the infimum of E is strictly higher than the supremum of E prime. Here's another example where the infimum and supremum coincide, but in all other spots, set E is going to be strictly higher. This is a non-example. So here, E and E prime cannot be ranked according to this strict order that we've introduced, but this is a case where E dominates E prime in the strong set order. So this is just to say that the set order that we're considering is stronger than strong set order. And in particular, it will imply strong set order, but not the opposite. So our goal is to look at the set of total surpluses that are induced in equilibrium, as well as the set of agent surpluses that are induced in equilibrium. So take some set E in the n+1 space. The set of total surpluses you can achieve is just going to be essentially the L1 norm of that vector. So I'm just going to look at what are all the different total surpluses that are induced by having a payoff profile within a set E. And our first result is the following. For any n greater than 1, so when you have competition, and for any search cost k, one of two things is going to happen. Either the set of total surpluses you can induce under a monopoly and competition are going to coincide, or the total surpluses you can induce under a monopoly is going to be strictly higher than the surpluses you can induce under competition, according to the set order that we've introduced. So this is saying either the two sets will always have the same total surpluses, or monopoly will have every outcome under monopoly will have a higher level of efficiency, at least weakly higher level of efficiency, than every outcome under competition. In particular, I can make this a bit stronger. For every n, there's going to be an open interval of flow cost such that for any flow cost in this open interval, the strict ordering is attained, where monopoly always achieves a weakly higher total surplus under every equilibrium than competition will. Okay? So this is the sense in which we say competition reduces efficiency here. So as I mentioned earlier, there might be more information provision in one setting than another, but that doesn't necessarily immediately translate to a higher level of agent surplus in that setting than the other settings. So it's also important to compare the agent's welfare. And
Teddy, can you go back? Can you tell us a little more about KN, like where it lies? I mean, so it's a subset, but is it low? Is it high?
It's high. So I think they'll come up. So essentially there's some regions where for a high cost, the only thing you'll be able to achieve under a monopoly would be a unique outcome where surplus is effectively being extracted. And that immediately means that, but yet you're still inducing the efficient outcome.
Mm-hmm.
And then when the cost is low, you essentially are going to be able to get Folk theorem in both cases.
Right. Okay. So yeah. Thanks.
Yeah. Okay. So in order to compare the agents payoff, again, take the set E. What are the set of agents surplus that you can induce from this set? Just look at the n+1 projection of this set. And our result is going to be the exact converse of what I showed you earlier. For any n greater than 1 and any cost of search, the set of agent surpluses that are induced under competitions either coincides with the set of agent surpluses under monopoly, or the competition's agent surplus set is going to dominate that of monopoly. And again, for some interval, this relationship is going to be strict. So the agent will be always will always be better off with the competition than under a monopoly, for any search cost in this open interval Kn. Okay. Okay. So let me go through some preliminary results first, and then I'll build up to the main results. Hopefully I'll be at least be able to show you the folk theorem result at very least. So the first thing is let's think about what is a marginal gain from search. So what would be the benefit of searching one more period? So let's imagine a world where the agent has an outside option that pays him a payoff of U. So you can think of this as a payoff guarantee. And we can ask, what is the benefit from one more period of searching according to some signal G? Well, you'll only find this beneficial if the draw that you get from G is higher than the guaranteed payoff of U. What is the expected value of that? It is going to be given by this integral, which you can rewrite using integration by parts as just a cumulant of the distribution of the survival functions here. And you can plot this as a function of this outside option. So as the outside option goes from 0 to 1, here I am plotting all the different values of search, or the benefit, the marginal gains from searching. The blue line is the marginal gains of searching when you have full information, and the red line is the marginal gains of information from when you have no information. One of the a few of the notable things here is that this function will always be a convex function of U, and it will always be a decreasing function of U. And it will be continuous because it's just the integral. And if you think of this not as just a function of U, but as a function of the G itself, then if G is a mean preserving contraction of G prime, the convex curve that you have for G will always be pointwise below G prime. And this is exactly what you see here. The red is always pointwise below the blue. And this is because no information is always worse than full information in the Blackwell order. But I can do this for any other information structure. So any arbitrary information structure G that I pick is going to induce some convex curve that is in between this blue and red line. Okay. And the set of all decreasing continuous and convex functions that lie in between these two curves, I'm gonna call that script C of F. Why is this useful? It's because it's a very useful way of thinking about what are the benefits of one additional period of search, and especially when you're trying to characterize the equilibrium outcomes. So now let's go back to a world where the agent observes G for free every period. And let's say that his continuation value in this stationary world is just U. So before that was just some outside option, but now I'm trying to endogenize this outside option. Well, what would be the value and the cost of engaging in one additional period of search? Well, one additional period of search has a marginal cost that is just the flow cost. So he's going to incur a cost of K. But what would be the value, the marginal benefit? It's just going to be this convex function that I just introduced, associated with the signal G, given that his outside option is just the same thing as his continuation value. That is the guaranteed payoff you will get if you continue searching. So what would be the agent's optimal thing to do? You want to equate your marginal cost to your marginal benefit. And that's exactly what the optimal, what his value, his continuation value will be determined. So there's going to be a unique solution to this equality, and let's call that this kind of calligraphic U that depends on both the signal that the agent is observing, which is the G, and also his cost. Graphically, all I'm going to do is just plot out a dashed line that is exactly equal to his flow cost, and everywhere this cost intersects with the convex curves, that is exactly what his continuation value is going to be. So the agent would want to stop searching. For example, if he's searching with full information, he has the blue convex curve that induces a continuation value of U upper bar K. So he should stop searching if he ever samples a good in this region And he should continue searching if he ever samples a good below this region. Okay. So the autarky payoff, this is going to be just the payoff associated with no information. That is exactly this value here. And the McCall payoff is what he would be getting if you were to search with full information. So that is exactly the solution from the standard McCall problem. And any other information structure is going to induce some continuation value between these two values. That means the net surplus from information in this world is just going to be the difference between what he would get with full information versus what he can achieve with no information. And all of these values are decreasing in the flow cost. So as the search cost decreases, he's going to have higher and higher continuation values, but also the net surplus itself is going to increase. Okay. Let me now talk about what are the possible feasible payoffs that we can see in equilibrium. So remember, the feasible payoffs is just some payoff profile in n+1. Well, no principal in this world can make a loss, because otherwise you could just offer the null offer. I sell you no information for 0 price every period. I can guarantee myself a payoff of 0. Additionally, the agent can always take the null offer that he has access to, so he can guarantee himself his autarky payoff. So that's given by an additional inequality. And then finally, the total surplus that can be generated in any equilibrium cannot exceed the McCall payoff, which is the highest possible surplus you could have if the agent were to search for free with full information. What this does is it gives you this kind of triangle. So this would be the triangle you would get if you only had a monopolist. But you can also think of this triangle as thinking about consumer surplus on the agent surplus on the horizontal axis, and summing up all of the principal surplus and thinking of the vertical axis as the producer surplus. So any region in this blue is a feasible outcome. So what is okay, so I'm trying to gauge how much time I have. So let's think about how to characterize the equilibrium outcomes in this world. Take this pair, alpha and beta, to be what we call simple strategies. So these are strategies that are independent of the history. For the principal, you're just going to choose some mixed strategy possibly over the different offers that you can make, which are price pairs and the signals that you observe. For the agent, there are 2 strategies that you have. The first one is your purchasing strategy. So you're going to observe some profile of offers, and you're going to choose a distribution over the offers that you're going to accept. And then you have a stopping strategy, which is given the profile of offers that you've observed, your choice to purchase from from at most one of the principals, and some signal realization that you see, what is the probability with which you stop? Okay. On top of this, we're going to think about these continuation payoff functions, which is a mapping from the offers that are observed, the choice that the agent makes from whom to purchase, and the signal that's observed into one of the payoffs that are feasible in this triangle that I showed you earlier. So let VJ be the principal's payoff and U just be the agent's payoff, given some pair of strategies and continuation payoffs. I'll skip the details because I'm a little low on time. But what we want to define is, so the goal here is to essentially use the APS construction of self-generation to be able to characterize what the payoff sets that arise in equilibrium are. So for some set that is in the subset of the feasible payoffs, we will say this is a self-generating set if 4 conditions are satisfied. If for every payoff profile in the set E, we can find a pair of strategies as well as a continuation payoff, such that first, the agent behaves sequentially rationally with respect to the continuation values that they get. So once I see any profile of offers as an agent, my choice from whom to buy and when to stop should be dictated by what I expect to happen in the future that is captured by the continuation value psi. So this inequality just basically will tell me that I should always be stopping if I expect my continuation values to be too low, and I should continue, I should stop if I expect my continuation values to be low, and continue searching if I expect my continuation values to be high. And I should be buying from the principle that gives me the highest expected utility given what I'll get conditional on my purchase choices. The second is that the payoff profile that we're considering needs to be generated by the pair of strategies and the continuation values that we're looking at. So yj must equal the actual payoff the principal will get if they follow those strategies, given the continuation value, and yn plus 1 should also give the agent the exact payoffs that they expect to be getting.
Teddy?
Yep.
So as clarification, so just to make sure, these alphas and betas are
Yep.
still restricted classes, lie within a restricted class of strategy profiles, right? They're the simple ones.
Yes, exactly. Yeah. So you're basically thinking within this period, what are the strategies that I will implement today? And then instead of thinking about a continuation play defined by the strategies and the possible outcomes that we're going to get through them, I'm just going to think of encoding that information into the continuation payoff function itself.
Okay.
The third is no principal has a profitable deviation. So that just says fixing what all the other principals offers are going to look like, no one principal is going to be able to gain by a unilateral deviation. And then finally, the continuation values must always lie within the set E. So this is exactly what's going to make it self-generating. Okay? It's essentially saying any kind of reward and punishment you're going to get is arising from behavior that will sustain any other payoff function in the set E itself. And the reason why this is useful is because of this connection with APS that I mentioned. The payoff set for any n and any k is going to be a self-generating set. And in fact, it has to be the biggest self-generating set that you can get. So any other set that is self-generating is going to be a subset of these equilibrium, of the entire equilibrium payoff set. Okay. So I know I don't think I have that much time, so I'm going to skip this part.
Teddy, we can perhaps extend 2-3 minutes over the, you have 10 minutes if you want.
I see. Okay. Then at least I'll show you how to construct any feasible payoff, and then I'll talk about the outcomes. Okay. So the first thing we want to do is let's think about how to generate some payoff function. So some payoff profile that is feasible. Okay. So our first result is take any feasible payoff profile, Y. There's going to exist a very simple offer. Let's call that O star, and I'll tell you exactly what O star is. And there's going to be a pair of simple strategies and continuation payoff with the following characteristics. Every principal is going to propose O star with probability 1. The beta, the agent's behavior, we're just going to allow that to be a sequentially rational behavior. So given whatever kind of profile of offers that you see, and whatever continuation value that you anticipate, the agent is just going to best respond to those strategies and continuation values. And then the additional thing is that in the event that every principal proposes the offer, the O star that they're supposed to, regardless of what the agent does, regardless of what the signal realization is, the continuation value is just going to be Y again. Okay. If these three things, so the lemma is there's some an O star and a profile of strategies and continuation values that satisfy these these conditions that actually generate Y itself. So Y would be able to generate itself if the principals essentially propose the same offer in every period, and the agent accepts one of these offers from one of the principals. So how do we construct such an O star? So remember this figure. The highest payoff that we can have is the McCall payoff, which is searching for free under full information. The lowest is the autarky payoff, which is searching with no information. And if a payoff profile is feasible, then the total surplus that we can generate must lie in between these two values. And so I'm going to just denote the total surplus by the L1 norm of the payoff vector. So I'm just adding up what every person is supposed to get. Additionally, the agent's payoff must be higher than its autarky payoff. So these are the constraints that are imposed by feasibility. We can't give you a higher surplus than McCall, and the agent cannot get a lower surplus than their autarky payoff. Okay? So our goal is to try to generate a surplus of this amount while only giving the agent a lower value of that surplus, only a share of that surplus. Now, what is the difficulty here is it is actually quite easy to find an information structure that can generate any of these total surpluses that we want, but that requires the agent searching in a very particular way. In particular, it requires the agent searching as if their continuation value is dictated by the total surplus, but we want to only give the agent a much lower utility. And that might mean the agent is going to search, is going to terminate their search too early. And we don't want that to happen. So what we're going to do is look at what are pass-fail signals. So this green line is the convex curve that is induced by a pass-fail signal that tells you that the object is a pass if its true quality is above some cutoff X, and it is a fail if its true quality is below this cutoff X. What is important to note here is that this green curve intersects the dashed K line exactly at the total surplus. So if the agent were to observe this pass-fail signal for free every period, the total surplus that will be generated is exactly this Y1, the L1 norm of Y. But we want the agent to get a lower utility. So we need to make sure that the agent isn't going to stop searching too early. And in this case, it actually turns out that the agent would search the exact same amount as if he was getting this much higher level of utility. And the reason is whether your utility as an agent is you're capturing the total surplus or you're only getting a smaller share of the surplus, you're going to stop searching only if you see a pass, which induces a very high expected quality, expected posterior mean. And you'll continue searching if you see a low or if you see a fail, which induces a very low a very low expected value, a very low expectation of the good. So both of these players are going to see a pass or a fail with the same probabilities. And therefore, if this agent was willing to continue searching, so is this agent. Now, the only thing remaining is to take whatever surplus we're not giving to the agent and give it to the principals. That's pretty easy to do. I'm just going to set a price that is a differential between what the agent is going to get if he searches for free versus what he would be getting if we wanted to get him this level of utility. So the gap between K and the actual surplus of the actual gains of marginal search from using this pass-fail signal. And then we're going to insist that all the principals offer this combination of a price and pass-fail signal. And because the agent is indifferent, he's willing to randomize in any way that distributes this aggregate producer surplus in just the right way so that each principal is getting exactly their YJ. And that generates the entire payoff profile. So why is this useful? It's because remember that we have these 4 stipulations for some set to be self-generating. And what we've just done is we've ruled out two of them as being immediately satisfied. For any payoff profile Y in E, I can find a beta that is sequentially rational that generates Y itself. So the only two things left to check for me is that no principal has a profitable deviation. So I'm generating this Y by insisting that all the principals offer the same pass-fail test in every period. I just need to make sure that that is actually what the principals end up doing. And then the second thing is I just need to make sure that the continuation values I'm promising are exactly within the set E. Okay. So I'm going to skip this part. But the one thing that I want to basically say here is for a monopolist, the only thing left to do is just make sure that the principals do not want to deviate. So this is the payoff. This is the set of feasible payoffs for the agent on the horizontal axis and the principal on the vertical axis. So if, for example, there's some value, let's say here, that is attainable as part of an equilibrium, then that must mean that anything above this point is also attainable as an equilibrium. And that's because if this point is an equilibrium, we've managed to convince the principal to not deviate from proposing this pass-fail offer in every period in every period. And therefore, anything else that's above here, we're sustaining through another pass-fail signal that would generate at least a higher level of profit. And therefore, if you were to ever deviate, we can punish them the same way we would be punishing the principal right here. So that means your equilibrium sets will always look something like this for a monopolist. It will be some sort of a triangular shape. And this allows us, this gives us quite a bit of structure to be able to find a fixed point operator that actually lets us characterize what all the self-generating sets will be. Oh, okay. So our result for monopoly is that you have a bang-bang equilibrium payoff set. And by that, we mean there is a unique K star such that if the flow cost is greater than K star, the only equilibrium outcome is full surplus extraction. And this is the outcome that we characterize in our other papers. So you can get this by just looking at stationary equilibria. On the other hand, if the K is small enough, then you can in fact get all the feasible surpluses as the equilibrium outcomes. So what that means pictorially is either you have only a single point in this feasible payoff space that will be sustained as an equilibrium payoff set, or everything is going to be an equilibrium payoff set. So let's move on to competition. Our results then is if you can get Folk theorem with a monopolist, then you get it also with competition. And the reason is, so the consequences here immediately give us at least our weak comparison in terms of efficiency and the agent's payoffs. And that's because for the monopolist, either the outcome is full surplus extraction, which is remember, it's on the Pareto frontier. So this is as high as possible that you can get, or you got everything. But if you got everything, then you're getting everything with competition. And if you're not getting everything with competition, then the only thing you'd be getting for monopoly is the perfectly efficient outcome. So monopoly will always induce a level of total surplus that is at least as high as whatever surplus you can get with any competition. The opposite is going to hold for the agent's value, because under monopoly, the agent's value is being fully extracted. And whenever that's happening, and otherwise you get any kind of any of the agent surplus that is feasible is also an equilibrium outcome, but that's also going to be the case with competition. I'm going to skip why we get that. And then the one thing to kind of remark is when you have a monopoly only, the way we constructed this equilibrium depended on punishing the principal when he deviates by punishing the agent whenever the agent accepts a deviation contract or offer, and rewarding the agent whenever he rejects a deviation offer. And what we show is this is really the only tool that you have with a monopolist. Now, when there are multiple principals, there is another outcome. That's the Bertrand competition. This is always an equilibrium where in each period, all the principals offer full information for free. It's very simple to kind of think about here. All the principals first are going to compete by offering higher and higher levels of information. There's a ceiling to how informative something can be. And then you compete by lowering your prices, and there's a floor to how low that can go. So what we're saying now is when you introduce competition, you now have two levers you can pull. You can still use only the agent to punish the principal, but now you can also use this additional level, which is if any one of the principals deviates, all of us get punished by going to the Bertrand equilibrium. And this is enough to get us the strict comparison. So Mark, as you noted, the Kn is not between 0 and m naught. It's between this K star that sustained uniqueness for the monopolist and m naught. So if you look at what are the total welfares, the set of welfares you can achieve with a monopolist, it is just the McCall set. It's just singleton. But for the competition, we can get a bigger set because now we have this extra lever that we can use to get a bigger self-generating set. And then the opposite holds for agent surplus. And that's essentially the main insight of the paper. Okay. I think
yeah, we're running. Yeah, probably we should wrap up and maybe if later we have time, we can.
Yeah. So that is basically all I had to kind of to say here. I would rather take questions and feedback unless someone is dying to kind of see the connection about their latest literature.
Okay, so yeah, maybe we can take a pause now, no, and open the floor, no, for Q&A. So I'm gonna suggest that either Mark or Alessandro, no, I mean, I don't know. Mark, for instance, would you want to make a final question or comment?
Sure. So this is very nice. I mean,
Thank you.
It's great. My one question, and it's given the way that you constructed these distributions, which is via truncations, I wonder if kind of a clever guess would allow you to handle risk aversion as well. So you obviously you'd have to, change the apparatus a bit, but in a sense, because truncations are, relatively easier to work with than like bipooling, and I wonder if you could. I suspect, in fact, that even if you had risk aversion, at least the qualitative features of your results would also go through, and that would be kind of cool.
I see. Okay.
Yeah.
You might be right. So we really have not thought at all about anything beyond the risk neutrality here. I think the one maybe additional complication is the kind of the Pareto frontier might no longer be this nice linear
right
set. And we use the structure that basically all you need is these 3 points to be able to get this fixed point operator. But there might be a way to kind of operationalize all of that and get a bigger result. Yeah.
All right.
So I have more, but I'll shut up.
Yeah. So if you, Alessandro, if you want, you can make a comment first, and then we can continue informally after the official end, if you want.
No, I mean, I think this could be a good transition into the more informal thing. I think this is great. I wanna learn more about it. I should read your first paper more carefully than than I think I have in the past as well. I just wanted to basically, I would like you to keep going, but maybe you can say a few more detail-oriented things, like for the case on the theorem that's on the slide. What is the role of n? Is there an homomorphism with k? You can maybe, if you wanted to make a point prediction, you could pick a point from the equilibrium set when it's not the Folk theorem, but you have competition, and tell us how the I don't know, maybe the firm preferred one or the principal's preferred one, and tell us how these thresholds change. Some this is not an applications question; it's more an applied theory question, but to see a little bit more of how this works. But otherwise, just great job.
Thank you. So we really, I think we still have quite a bit of work to do in terms of especially the comparative statics with the K. One of the difficulties is we have a characterization of the full equilibrium payoff set with a monopolist, but we only have a partial characterization for the competition. And so given that partial characterization, we can say something about how the payoff sets change when the number of principles changes, but that's essentially not enough to get us a result that, for example, says as the number of competitors increases, how does the set of welfare that the total surplus that can be attained in equilibrium, how is that changing with n? We can only say that for a particular subset, and we don't really know what happens beyond that subset. But so essentially, within this kind of restricted class of equilibria that we're looking at with competition, it's actually like a bit surprising when you go from monopoly to two competitors, then the result continues to apply. And in particular, this Kn is big because take any kind of let's think about symmetric equilibria, for example. Take whatever surplus that the principals capture and they're splitting it equally. And I'm telling the principals if that they ever deviate, I'm going to punish them by going to Bertrand. And because they're only splitting the surplus across the two of them, that's a fairly credible threat that prevents deviations. Now, if they're splitting it between 100 of them, then already your on-path payoff is so low that deviations become very attractive, and this Kn starts to shrink. And it seems that then you start going, in fact, in the direction of monopoly. So you basically have this kind of non-monotonicity where you get a jump when you go from n equals 1 to n equals 2, but then it starts to kind of go back in the direction that the monopolist was in. But we would love to be able to say that that's actually true for the entire equilibrium payoff set, but we don't know that yet.
Maybe now is actually a good time to stop the official part and stop the recording, and then we can continue talking. So yeah, let me just take a second to thank you, Teddy, for the great presentation, and the panelists Mark and Alessandro, and also Bobby for looking at the chat. And yeah, everyone come back next week for our last seminar of this term with Piotr Dworczak. Yeah, thank you very much.